just remind you what we said. I reviewed for you the classical black hole geometry, and I said, the physics that we're going to discuss is not the physics of this whole geometry, but the physics of what happens at late times. And then I said, at late times, the horizon is, we can write down a simple metric. That metric has the form, maybe I can write it down again. ds squared is minus f of r dt squared. This is not the metric of the full black hole as it forms from collapse, but it is a metric of the late time part, which is the shaded part. And then I said, this metric looks like it has a singularity near the horizon where f of r goes to 0, but that singularity is just a coordinate singularity, as you can see. If you move to these coordinates, where you define this tortoise coordinate dr star, and in these Kruskal coordinates u and v in this way. And then, so that was the second point we made. And the third point I made was, imagine some scalar field, which for us was just a prototypical quantum field. What I said was not relevant to specifically a scalar field or some other kind of field. And I said that you could solve the wave equation. It's convenient to solve the wave equation in these r star and t coordinates. And this wave equation simplifies near the horizon. And you get two solutions which look like e to the minus I omega t plus r star and e to the I omega t minus r star. One of them, the one which goes like t plus r star, where when t increases, r star must decrease, is a solution that is an ingoing solution. You can think of it as ingoing, and the other one is an outgoing solution. The way you plot it on the Penrose diagram is actually goes parallel to the horizon. If you push it out a little bit, it goes out. Okay, but so you can think of these waves as moving this way and the others as moving this way, and these are the two solutions that we discussed. So those are the 3 points we made in lecture 1. I now want to describe the derivation of Hawking radiation and explain how we arrive at a paradox, or naively a paradox. So are there any questions about this part, the material we've covered so far? Okay, good. So if there are questions, please ask. As I said, it helps me get feedback, even if they're short questions. It just helps me get a sense of where we are. So now I want to say a little bit more about these solutions. In fact, it's related to this point about boundary conditions that was made earlier. We found these solutions, and now we want to quantize the field. Okay? So the point of finding the solutions is finding the solutions helps us quantize the field. So we want to write down some creation and annihilation operators. So you want to write down a field that has the form. I'm going to write a sum, okay, over frequencies and angular momenta. It's not really a sum, okay? The frequencies are continuous. So I should really like integral d omega by square root omega. This is just shorthand for that, okay? I'm writing sum of omega L, but please be careful when you write down the full formula. If you want to write down carefully, you should write down d omega by square root omega, put all the 2 pi's. I'm not going to do that here, okay? And I hope that doesn't confuse you. So, F in of r star plus okay. So what is this, so what I've done here is I've said that if quantize the field, so how do you quantize the field, right? You take the solutions of the equations of motion and you promote, it's a linear field equation we are trying to quantize. Of course, you can go higher order in perturbation theory. And you take the coefficients of those solutions of the equations of motion and you convert them to operators. Okay? And so these A omega L's and these B omega L's are now operators. Okay? And this is the e to the minus I omega t. This f of I and r star is going to be related to the ingoing solution, although I'm going to say one thing which is a slight subtlety which you should keep in mind. And this is the part in the sphere. Okay? So this is how you would quantize the field in the black hole background. Now, let me say a little bit about this f I and r star and this f out r star and how they're related to these simple modes that we found here. In fact, this is related to this issue of boundary conditions. So what we really need to do is do something a little more subtle. Is we write down, let me just get my conventions correct. Yeah. So in my notes, I have A and B oppositely. Let me try it. Yeah. is equal to, some h omega L into e to the I omega r star minus I omega r star. Okay. And f out omega. I'm just writing down a formula and I'll explain in a minute what that does. Okay. Okay. So when I wrote this f out omega, remember I said there were two kinds of solutions you could find. As you went to r star goes to minus infinity, which is also r goes to r horizon. Remember I said the wave equation simplifies, right? So wave equation simplifies, you can have only two solutions, e to the minus I omega r star, e to the I omega r star. However, the solutions that are really that really correspond to canonically conjugate solutions are not really e to the minus I omega r star and e to the I omega r star. Rather, you take some solution which looks like some number, some c number h omega L, this is not an operator, times e to the minus I omega r star, and some other number which looks like g omega L times e to the minus I omega r star plus e to the plus I omega r star. What is the property of this solution? Why do you take these funny numbers? Why do you have to take these complex these linear combinations? The reason does have to do with boundary conditions, because this solution f out r star has a property that when r star goes to plus infinity, it goes to simply e to the I omega r by a factor of r to the d minus 1, which let me get from my notes 1 second. Uh, into r to the 1 minus d by 2. Okay. This factor is not important. What's important is that, in 4 dimensions, this would be e to the I omega r by r. It's just the outgoing spherical wave. Okay. It's the fact that what we demand is that this solution, as r star goes to plus infinity, goes to e to the I omega r star. It doesn't matter if I write r or r star. Okay. So we want a solution that as r star goes to plus infinity becomes purely outgoing at plus infinity. Okay. And once you fix that and you fix this coefficient to be 1, then basically you're forced to say that you have to take the solution to be 1 plus some component of the ingoing solution at the horizon, so that at infinity it becomes purely outgoing. Okay. So what you want is this solution at infinity should be purely outgoing, and to do that you have to take it to be some combination of outgoing plus ingoing here. Okay. And once you do that, then you just ask, what is the orthogonal solution, and that's this solution. And the constraint between h and g is that mod h square plus mod g square has to be 1. Okay. So the way you should think of these solutions is as follows. Let's go back to this diagram, which we'll make reference to many times. You can think of this solution as this outgoing solution as f out specifying data here. And this solution f in, it specifies data here. So what we are doing is we are imagining that on the future you can specify data on two parts of the future boundary. I see that whoever wanted me to write in blue has. Is this blue? The blue chalk is just gone. The blue is gone. I don't even have that option now. I know there was a preference, but now it's been imposed by. It's fine. It's fine. Oh, thank you so much. If it's there, it's great. I'm just using it sparingly, just for this. Yeah. So what we've done is we've said that you can write the future data in terms of the data here in blue and the data in black. Okay. So you see, usually we want to specify data just on a space-like slice. Now on this space-like slice, I've broken it up into two regions. One more set of modes is specifying data on this slice, and the other set of modes is specifying data on this part of the slice. Okay. So these are what I'm calling f out, and this is what I'm calling f in. And the only subtlety to keep in mind is that what we are calling the outgoing mode is really a combination of some ingoing and outgoing part of the horizon, so that it becomes purely outgoing at infinity. Okay. And what we are calling the ingoing mode, it will become some combination of in and out at infinity. Okay. So you specified something to be purely ingoing here and purely outgoing here, and that's an orthogonal space. Okay. Okay, good. Now notice that I can think of these solutions also as doing the following. Okay. Okay. So notice that what's appearing here is e to the I omega into t plus r star and e to the I omega into t minus r star. Okay. And look at the formulas we have for u and for v. So I can write this factor of e to the I omega t plus r star into omega as v to the minus I omega by k. You see this? Okay. And I've put some tilde here because there's some proportionality constants that I'm not going to be bothered about. There was a proportionality constant here. Okay. And that you can think of as going into a redefinition, but that has to do with the fact that I put a tilde here. Okay. And in any case, we're not being careful of overall constants. But do you see that the dependence on t and r star here becomes a dependence on v? And the dependence on t and r star for the outgoing part, for this part, becomes a dependence only on u because it's a dependence on e to the I t minus r star. Okay, you see this? And then there is, of course, this part. Sorry, I should have written. Sorry, there's a YL omega I forgot to write. Okay, and this whole part is now multiplied with some spherical harmonic, which was there as well, and then there's the Hermitian conjugate. Okay. So notice what's the interesting thing that's happening here. The interesting thing that's happening here is that the solution of the wave equation looks like a solution of the wave equation in 2 dimensions. I know in the preschool some of you also studied Rindler space, but these are the modes that appear in Rindler space. Even though we are in a higher dimensional space time, when you look at the wave equation near the horizon, you find that the solution of the wave equation looks like a solution of the wave equation in Rindler space times some spherical harmonic, but the spherical harmonic is not entering here, right? Because this part of the dependence is completely fixed by this one parameter omega, and then the spherical harmonic is just going along for the ride. It's there, it's important, it's telling you what the field is doing in the sphere. But when you're near the horizon, this has to do with the fact that, the space-time effectively separates into some 2-dimensional space-time near the horizon and some sphere. Okay. And that's why the physics of Rindler space is so useful to understand the physics of black hole horizons. Okay. Okay, so this is still restating this point. Okay, we are still playing around with this point. It's the fact that near horizon the wave equation separates and it becomes, you get one part which looks like e to the I omega t plus r star, another part that looks like e to the I omega t minus r star. This term is the one that's a factor of u, and this term is the one that depends on v. Can you see? Okay, so maybe I can take questions while we wait for light to come on. Yeah. Are there questions? Sorry, what? Is someone asked a question? You had a question, yeah. The last part was just saying that remember the solutions look like e to the I omega t minus r star and e to the I omega t plus r star and e to the I omega t minus r star. I've just rewritten that in terms of u and v because notice the same combinations appear in u and v. Yeah. Okay.
What terms is that summation? Bible?
No, the e to the I omega plus I omega t went in the plus Hermitian conjugate. So plus HC means plus Hermitian conjugate. And so all the e to the plus I omega t terms go into that. Why have I separated it this way? Because the terms that multiply e to the minus I omega t are what we call the annihilation operators. And then there would be terms that multiply the e to the plus I omega t, and those would be the creation operators. Okay. So when you want to write down the field expansion, you only need to keep track of the annihilation operators because the creation operators are just the Hermitian conjugates of that. So all of those go into the plus HC. So the e to the minus I omega t always has the same sign, but the e to the minus I omega r star and the plus I omega r star have two different signs. There's minus I omega r star plus I omega r star. Okay, because totally you have 4 different possible signs. So you have to keep track of 2 with the annihilation operators, and then you get the creation operators, the Hermitian conjugates. Okay, is this clear or am I losing people? If I'm, if I get no questions, I get the sense I'm losing people. It's not clear? Yeah. What is not quantized? The field is quantized. I now only have to impose some commutation relations which I haven't written down. But what I need to impose is I'm going to put a tilde here because I haven't kept track of constants. So you might get a factor of 2 pi or whatever. That doesn't matter. And similarly for B, the field is now quantized. Same. Yeah. So the field is A dagger. It's not plus. Sorry. I don't know how to share. Yeah. What does dagger mean? Sorry. Huh? Yeah, A's and B's are commute to 0. Yeah. So A and B are 0. This is not a complex scalar field. It's a real scalar field. And it's a real scalar field. It's not a complex scalar field. A complex scalar field has creation operators for one and destruction operators for the other. The way I quantize it, this is just a real scalar. It's not a complex scalar. Okay? You can still have, the fact that it's a real scalar doesn't tell you that you can't have 2 different kinds of creation annihilation operators. Okay, you can always take a real scalar field and you can always break it up into modes on one side and modes on the other side. You could always have done this even in your QFT course. You could always have said, I'll call the modes with KZ positive, the left moving modes, and ones with KZ negative, the right moving modes. And I'll call those 2 different kinds of creation annihilation operators. So don't get confused with the fact that you have 2 different kinds of creation annihilation operators. You can always take the creation annihilation operators of a field and break them up into 2 classes. Okay. Here we've broken them up into 2 classes based on whether they have positive or negative radial momentum. Okay. So the breaking up is based on the sign of the momentum in R star. So I can always break up operators into 2 classes like that. Yeah. And the question about boundary conditions, I hope is now answered. That question was imposed here. Okay, this was the boundary condition we had to impose. Okay. If I'm losing someone, I'm happy to explain some more detail. If I'm losing at least half the audience, so if there are questions, I would appreciate if you ask. Yeah. This had to do with this had to do with what we derived. It had to do with the fact that when you go um, well, so is a mathematical derivation of this part clear or not clear? The mathematical derivation of this part is what we did at the end of the last lecture. Okay, so then these are just numbers. You have to put them in for normalization, and you have to take some linear combinations to get the right boundary conditions at infinity. I have not told you what these numbers are, but you can see, if I take a purely ingoing wave at the or at the horizon, or purely outgoing wave at the horizon, as that wave goes out, travels out from the black hole, some part of it tends to scatter back. So something that's purely outgoing at the horizon doesn't remain purely outgoing at infinity because some of it scatters back. So if I insist that it's purely outgoing at infinity, I have to take some combination of outgoing and ingoing at the horizon to get purely outgoing at infinity. That's what is happening here. You take a combination of outgoing and ingoing at the horizon so that it gets purely outgoing at infinity. This is like a scattering problem that you have done in one-dimensional quantum mechanics. It is really that problem mathematically. If you have a potential and you're scattering, and I say that I have purely outgoing on the right, on the left you have to take some combination of in and out. That's the only way you'll get purely out. That's what's happening here. So, okay. So it's the same for both. On the other side, so this is, in fact, the mathematics of this is exactly the mathematics of solving scattering in one dimension, which you have presumably studied. Okay. Other questions, sir? Yes, these commutation relations come from equal time commutation relations. So you're right that to get these commutation relations, what I should really impose is that phi of t and phi of t and at r star and r star minus r star prime is a delta function, right? So what I should really impose is that phi at t r star omega and phi at t r star prime omega prime is a delta function in r star minus r star prime delta of omega prime, and there's a factor here, square root g, I think. And when you impose this, you get these commutation relations. Okay. So maybe I've skipped a few steps here, but these are the standard equal time commutation relations. Phi and phi dot, sorry. Phi and phi dot. When you impose the standard equal time commutation relations, and I should probably also put an I. When you impose the standard, sorry, 1 second, let me, yeah. Okay, there might be some factors I might be missing or minus signs. So let me put a tilde here to not get caught up in that. The point is that the phi's and the phi dot imposing the equal time commutation relations gives you these commutation relations between the creation and the annihilation of this. Okay. Okay, is this clear? Okay, so I haven't said anything very deep. All I said is we got two solutions and then we quantize the field in terms of ingoing and outgoing modes. Okay, now I'm going to sketch for you the derivation of Hawking radiation in terms of these fields. In fact, the derivation of Hawking radiation, once you've got these fields, is pretty simple. And I'll give you a reference to a place where you can see the details of this calculation in more detail. It's the way I'm presenting is not the way Hawking initially derived Hawking radiation. But, I think it's the simplest way that brings about the physics of Hawking radiation most clearly. And so given this field expansion, I'm now about to derive for you how Hawking radiation, works. Okay. So notice that, let's say I want to get, let me write here. Let me write here. Let's say I want to get the 2-point function of these b's. Okay. Why is the 2-point function of these b's important? The 2-point function of these b's is important because the 2-point function of these b's tells you what is the radiation that goes out here. The 2-point function of the b's tells you what is the component of the outgoing radiation. Right? So, if I compute the 2-point function of the b's, then that will tell you how much radiation is going out. And the 2-point function of the b's, you see, can be computed by taking this field expansion near the horizon, okay, and somehow extracting, the part that depends only on u. You see, the field expansion is broken up into some part that depends on B and some part that depends on A. And the difference between these two parts is that the B depends on U and the A depends only on the V. Okay. So, if you could compute this 2-point function is related to let me now get the signs right into to be. So, if I take the field near the horizon, okay, this is not a precise equation because I've lost many factors, which I don't want to keep track of. And I refer you to this paper, which will keep track of all the factors of the 2 pi's and so on. Let's say I take the field near the horizon, okay, and I differentiate it with respect to u. Look at this expansion. What happens? If I differentiate this field with respect to u, then you see that this part simply drops out. You see that? Because it does, the derivative with respect to u just kills this, right? So, if I take the field very close to the horizon and I differentiate it with respect to u, then this part drops out and I'm left only with this part, right? Okay, good. Then I take the field and I do that also for the other, for this other field operator. I take a 2-point function of the field, this differentiated with respect to u and this differentiated with respect to u prime. Then I integrate this with minus u to the I omega by k. That pulls out a particular Fourier mode in this expansion. You see, this Fourier expansion looks like minus u to the I omega by k, and it might not look like a Fourier expansion to you, But realize that minus u to the I omega by k, I can just write as e to the I omega by k into log of minus u. And don't get confused by the minus u part, okay? You can write this as log of mod u if you like, because u is negative outside the horizon. Remember the way we set up our coordinates. So don't get confused by the fact that you have a minus u here. This is just e to the I omega by k into log of minus u. So you can think of this as a Fourier transform, but with log of minus u being the variable. Okay. So what I'm doing by means of this integral and integrating over u is pulling out a particular frequency. And what I'm doing by this integral and integrating with respect to u prime is by pulling out another specific frequency. You see that? Okay, you have to be a little careful of how the factors of u work out, and the fact that when you do this Fourier transform, you get a delta function in log of u, which is like a delta of u minus u prime into u. But you also have to be careful of some other factors that come from the derivatives. Okay, that's why I put a tilde here. Okay, and there are various other factors of 2 pi's and so on. However, there's a very important fact which you should realize, which is the physically important fact, which is usually it would not, if I wanted to write down a formula of this kind, I would have to do an integral over all u. However, here, this expansion that I've written down is valid only near u equal to 0, because it's a near horizon expansion. Yet, I claim that a formula of this kind is sufficient to give me the 2-point function of these modes. And the reason for that is that this region near the horizon actually has a very large number of oscillations of u. Because in this region near the horizon, log of minus u goes over an infinite range in an infinitesimal range of u. This is the basic physics of how, basic mathematics of how Hawking radiation is derived. It has to do with the fact that when you want to extract the 2-point function of these modes, you can do an integral of the 2-point function of the field, but in a very narrow region around the horizon. And why can you do that? It has to do with the fact that the u variable goes through an infinite number of oscillations near the horizon, because log of u goes from, over an infinite range as u goes over an infinitesimal range near u equal to 0. Okay. Do you understand this fact? That this integral can be done in a small range about u equal to 0. You don't have to do this integral all of infinity to extract a given Fourier mode. So if you open this paper, you will find that there's a function in this paper which is defined, which has a t of u. That t of u is some smearing function that basically starts at 1 near 0 and then dies off smoothly at u equal to epsilon. Okay. I haven't written that function here, but you should think of this integral as going from u equal to 0 or slightly away from 0 up to u equal to epsilon, not going over all ranges of u. And that's important because this expansion itself was only valid near u equal to 0. Okay? Okay. So, if I could compute this 2-point function and I can do this Fourier transform, then you would have been able to derive the 2-point function outgoing here. Now, you could have said, well, what have you given me? Because you've converted this problem of computing this 2-point function into some problem of computing the 2-point function of the field, but I don't know how to compute the 2-point function of the field. However, in one limit, you do know how to compute the 2-point function of the field. And that is in the limit where you take 2 points not only close to the horizon, but also close in the v coordinate. Not only at small u, but also close together this way in the v coordinate. In that limit, minus u prime and v minus v prime are small. And a small here, small is never a meaningful thing unless I tell you what the scale is. Okay, so when I say they're small, I mean they're small compared to all the other dimensionful scales in the problem, such as the horizon's radius, such as the mass, and so on. Okay. When this is small, then we know what this 2-point function is. And also when omega minus omega prime, omega is close to omega prime. Yeah. You don't want me to write here? Okay. Oh, okay, sorry. Let me write here. Okay, so what I wrote there was when u and u prime are close and v prime are close and omega prime are close. All I want to say is that if you take this 2-point function, this 2-point function, okay, goes like 1 by s to the power 1 minus d by 2, where this s is just the square of the geodesic distance. Okay, this is the thing that would have gone. Sorry, did I write the? Maybe I should. So, so this in d equal to 3 would be just the thing that goes like 1 over s, okay, which is just 1 over x squared. Remember that the 2-point function at very short distances is just, it's fixed. Okay? So if you take the field and you go to very close by, you take a field of this kind, you go very close, that 2-point function doesn't care about the curvature and the geometry. It's always 1 over x squared. Okay. So this s, which is the square of the geodesic distance, always controls the behavior of the 2-point function when you're very close. In that very close limit, it doesn't matter whether you're in flat space or whether you're in the black hole geometry. What is the difficulty in computing the 2-point function in the black hole geometry? There are various difficulties. It has to do with the fact that the black hole geometry is curved. It has to do with the fact that the field itself might have a mass. It has to do with various other effects that might appear at long distances. But if you go to very short distances, that behavior of the 2-point function is just fixed because it's just like computing the 2-point function in flat space. Okay? So if you go to u being very close to 0 and also v being very close to 0, then you do know what this 2-point function is. Okay? So this expression you can evaluate in the limit when v is very close to 0. And that's a perfectly good regime in which to evaluate this 2-point function. You can evaluate it at any v, but in particular in the regime where v is also very close to v prime, you know what the form of this 2-point function is. You know it's given by this. Therefore, in that regime, you can evaluate this integral. And this is basically the exercise that Hawking did. And he found that this 2-point function indeed was just given by e to the minus beta omega by 1 minus e to the minus beta omega into delta omega minus omega prime. Okay. And there's of course delta LL prime. Okay. So Hawking's main point was to evaluate this 2-point function. Okay. And let me just explain what went into this. Okay. This might seem like a slightly mysterious derivation where this beta is 2 pi over kappa. So I have not performed this calculation for you, and I'm not going to perform this calculation for you because this will take us too far afield. But the details of this calculation are given here. Okay. I'm just going to explain to you what the physics went into it. Beyond that is just a question of doing a Fourier transform. Yeah. Omega and omega prime are here. Yes. So I have to compute an integral over omega and omega prime. This. Yes. Omega is inside of delta. It's omega minus omega prime. No, it doesn't matter because it's delta, no? So I can write a function of omega and omega prime. How does it matter? What you want me? I can write this. It's the same. It is equal, no? Omega is equal to omega prime. So function of omega is the same as function of omega prime. Right? Like all I'm saying is this. That's all that's happening, yeah? Okay. Yeah. This correlation function, this is the short distance behavior of the field. Okay. This correlation function is not a statistical mechanics thing. It's a correlation function that in that you might be familiar with. It has to do with this. In 4 dimensions, you're probably familiar with this correlation function. This goes like 1 by t squared minus x squared. Have you seen this? This is this s. Okay. So it's this correlation function for a massless field for very short distances. Yeah, this is a thermal correlation function. That's right. So this is familiar because this is the 2-point function of an oscillator that's thermally occupied. Okay. And of course, if you use the commutation relations, you will find that B omega L dagger. What will it be? Okay, I'm going to give you 1 minute to try and work this out on your own. We have the commutation relations on the board, and I told you what B omega dagger B omega was. So you have to work out what B omega dagger is. Okay. So 1 minute is up. So of course it's this almost the same expression, except I'll write it here so you can see. Is 1 by 1 minus e to the minus beta omega into delta omega minus omega prime delta LL prime. Okay. So remember, this is, the ratio of these two is sometimes called the KMS condition. If you give me B omega dagger B omega, that's e to the minus beta omega, and B omega dagger is 1 by 1 minus e to the minus beta omega. Okay? Yeah. Well, the Weikmann function is just this correlator. That's just a 2-point function. So this Weikmann function just means you take a 2-point function and you don't order it. You don't put time ordering. You just write down one operator on the right, one operator on the left. So this 2-point function is indeed the Weikmann function. It actually has to do with some I epsilons that I haven't been careful about that I'll have to put here. You'll get a T plus I epsilon here. This is the Weikmann function. This is just a thermal 2-point function. It's just a value. It's a function of oscillators. Okay. Now, all this might have seemed a little mysterious. You might have said, and so I'm going to take a step back and explain the physics. Okay, first let me review the mathematical derivation, which I've only sketched for you. And as I said, please go look at the paper which will do these calculations in detail. And so I'm just telling you what. First, I'll review the maths and I'll explain the physics. Okay. So what did we say? We started this lecture by saying that near the horizon, the wave equation simplifies. So we get these two solutions, e to the minus I omega r t minus r star, e to the I omega t minus r star. Therefore, I said, when you quantize the field, you get something which looks like some power of u to the I omega by k plus v to the I omega by k, and something else, some other oscillator into v to the minus I omega by k. So you get two kinds of oscillators. One is this oscillator, one is this oscillator. Okay? And then they are multiplied with some function of omega. But this function of omega doesn't talk to this power of u. Okay? Is that clear? This part I hope should have been clear. Till here we derived everything in detail. Is this clear or not, this expansion? Okay, good. Then I said, aha, now I have a bright idea. I want to compute the 2-point function of these b's. Why do I want to compute the 2-point function of the b's? Because these b's were defined by the boundary condition that they were outgoing modes. So if I compute the 2-point function of the b's, it tells me what is the occupancy of the radiation that comes out here. Right? So how can I compute the 2-point function of b's? Well, I notice that the field near the horizon breaks up into something of u, some power of u plus some power of v. So I take a derivative with respect of the field with respect to u and the field with respect to u again. And I take the 2-point function of the field with derivatives taken. That means that any contribution I would get from A just drops out. And whatever contribution I get will give me directly the 2-point function of b's. The b's here come with a u to the I omega by k. So in fact, I have to take this and I have to multiply it with a u to the I omega by k and u to the I omega prime by k, do an integral over u. And when I do an integral over u, I will pull out the 2-point function of particular frequencies. Because this 2-point function receives a contribution from all frequencies. By doing this integral, I'll get a contribution only from specific frequencies. Okay. But now, I also notice that I noticed two important things. First is that you would have said, okay, big deal, but you don't know this 2-point function for all values of u. And so how are you going to do this integral? But I noticed that this 2-point function, I only need to do the integral in an infinitesimal range near u equal to 0. I only need to do it in an infinitesimal range near u equal to 0 because the field oscillates infinite number of times near the horizon. Okay. So I only need to do the u integral in a small range near u equal to 0. I noticed that, 1 point. Second, I noticed that I can, you might still say, well, fine, okay, maybe you want to do it in a small range near u equal to 0. But near u equal to 0 just means I'm close to the horizon here. What about the separation in this direction? Well, because this formula doesn't depend on v, I can also do the integral for small v's when the points are just close to each other. And I know what the 2-point function is when the points are close to each other. I know it's given by this. Okay. It's just given by, if you like, just be in 4 dimensions. I know if you take these points very close to each other, I know the 2-point function is given by this. It's just 1 by t square minus x squared. So if I just set up some small coordinate patch where things look flat, okay, and I compute what the 2-point function is, then I know what the 2-point function is going to be given by. Okay. This, by the way, in the uv coordinates would look like 1 by uv minus omega squared. Okay. So then what do I have to do? I just have to take that 1 by uv minus omega squared, okay, and I have to differentiate it and I have to do this integral. So we've almost done all the steps. All I have to do is take this, write this as 1 by uv, you see t square minus x square is just u into v, and then there's a spherical coordinate I have to keep track of. Okay. So it's all I have to do is take that 1 by uv minus omega squared and then do this integral after doing that differentiation. That integral I have not done for you, but I'm telling you that if you do the integral, you will find this answer. So it's just a question of doing one integral, which I have not done for you, but other than that, you will find this answer. Okay. Okay. Are the steps clear apart from this last integral that I didn't do explicitly for you, but I told you you'd get this answer with beta equal to 2 pi by k. Although I did not do this integral for you, I've given you all the other steps and you can see how the integral is done by opening this paper. Okay, is at least a sketch of the derivation clear? If people are getting lost in what the steps of the derivation are, please ask me. I'm not giving you all the details. Yeah. No. This k is a k that has been appearing everywhere. There's no Boltzmann constant here. Yeah. This k is a surface gravity k. So, sorry, there's no Boltzmann constant always set equal to 1 for me. So, c is 1, h bar is 1, Boltzmann constant is 1. This k is this k that's been appearing here. I would have written kappa except my handwriting doesn't permit me to make a distinction between kappa and k. So, it's just k. Okay. Are there any questions about the sketch of the derivation? And I also want to explain some of the physical intuition that went in. Yeah. It is the temperature. This beta is the temperature. You see, this beta is the inverse temperature. You see, this 2-point function, which I'm going to say a little bit more about, is a 2-point function you'd get for oscillators at a temperature which was 1 over beta equal to 1 over t. So, what we have done by means of this derivation is related the surface gravity, which was a geometric concept, to the temperature. Okay? And I've given you all the steps except for doing this integral explicitly, which I haven't done. I haven't told you how if you integrate this, you will get this, which looks a little surprising. But it is true. If you integrate this against u, write it in uv coordinates and do this integral, you will get this. It's Mathematica will do it for you. If you put the integral into Mathematica will do it for you. Okay. Okay, let me explain the physics. You might be getting a little lost, right? What did we do? I mean, how are we getting this magic derivation that's relating, this geometric quantity to some thermal occupancy? So the point to realize, and that's a point that's emphasized in that paper, is that first of all, this is something that's not, what we used here. The fact that you have thermal occupancy is not actually special to the horizon. Anytime you have a null surface, maybe I can go there. Anytime you have a null surface, so you don't mind. Yeah. Ask you what is thermal occupancy. What is thermal occupancy? Okay. 1 second. Let's say you take a simple harmonica. Oh, okay. Let me answer that. Let's say you take a simple harmonic oscillator, right? So it has some Hamiltonian. Let me write it as omega a dagger a, right? You can compute then trace of e to the minus beta h of a dagger a and trace of e to the minus beta h of a dagger. You will get those answers. Okay. Yeah, this is the definition of thermal occupancy is, so you have to put a 1 by z beta and 1 by z beta, where z beta is trace of e to the minus beta h. Yeah. This is what what we use in statistical mechanics to compute the expectation value of the number operator, and this is also the number operator plus 1 in at a finite temperature. Right? This is so with this Hamiltonian, you compute that partition function and you compute the expectation value of the number operator, and you'll get that answer. Look, this beta is 1 by k Boltzmann into t. That is 2 pi by k. That k has nothing to do with Boltzmann k. Okay, so please don't get confused between that k and the Boltzmann k. This beta is 1 over t. Okay, Boltzmann constant is 1. Okay, yeah, so this tells you the thermal occupancy at a temperature T, and beta is related to 1 over T. There's no Boltzmann constant anywhere here. What we have now done is said that the occupancy of the outgoing modes is related to a temperature, and that temperature is given by 2 pi over k, where k is the surface gravity. Okay, so that's the Hawking derivation. It is telling you that the black hole is radiating with some property that's proportional to surface gravity. So you can think of the surface gravity as a temperature. Okay. No, we didn't know. Let's say we just did the calculation. We found this. So Hawking just did the calculation. He found this. This is not exactly a calculation he did, but in modern language, this is how you phrase it. The fact that you get B dagger B, you knew, right? That we derived. Because you took the field, you expanded it in B, you took this derivative, so you'd get B dagger B. The fact that you'd get this answer, you didn't know. But then you put in this value for the 2-point function, you put it here, you have to do some integral with u. You do that integral, you'll get some answer. You'll get some answer, right? It happens to be this answer. I've not done the integral for you because doing the integral will take half the lecture. So I don't want to do the integral analytically, but it's not hard to do. You have to basically pick up some poles and so on. If you open this paper, you'll see how to do the integral. But if you're willing to believe me that integrating that against this gives you this, then you'll see the Hawking. Then that's the Hawking derivation. Because this B dagger B tells you the occupancy of the modes that are going out. This B is multiplying the outgoing modes, right? It's multiplying what I called F out. I had written it here, but I erased it. So B was multiplying F out. So it's telling me that the part of the field which is outgoing at infinity is occupied in a way that's thermal. If you count the outgoing photons and you look at the number operator, that number operator is distributed probabilities. Do you see? Is this clear or? Yeah.
The field phi, is it just a stand-in for a generic field?
Mm-hmm. Yes. It's just a generic. Thank you. It's a stand-in for a generic field. Thank you. Yes. The field phi is just a stand-in for a generic field. If you did this for photons, you'd get exactly the same answer. This 2-point function is pretty universal, and you'll get the same answer. You will just have to keep track of some extra indices.
So can we heal this because with that pattern find out that upper is?
Yes. That's the Hawking derivation. That the surface gravity is proportional to that the black hole radiates at a temperature is given by the surface gravity. No, actually, the larger the black hole is, the smaller its temperature, but we'll come to that in a minute because surface gravity actually drops off its size. Okay, just before we come to that, I want to explain a little bit of the physics. You might have thought that some of this was kind of magic, right? What was the physics that went into this? So, in fact, the physics that goes into this is the following, and you should realize this kind of trick that I played. I spent so much time saying to you that the horizon was not something that was special. That's what I spent half of the previous lecture telling you. Then I said, oh, look, the field equations, simplifies near the horizon. And then I said, look, you can do this derivation and you find some answer for the outgoing modes. But if I told you the horizon was not special, you could have come and told me, okay, you just spent the lecture telling me the horizon is not special. Let me just draw a light ray somewhere in the middle of space. This is a light ray, okay, just 45-degree right. And let me try and set up the coordinates which looks just like the horizon because you said the horizon wasn't special. And let me kind of extract the modes that are outgoing here. Near this light ray, I can define some modes here. And so are you saying these would also be thermally occupied? And the answer is yes, they would be thermally occupied. Okay? The answer is if you define these modes, and you define modes here that went like u to the I omega, where u equal to 0 was this surface, then those would also be thermally occupied. So you take any light ray in the middle of Minkowski space and you define some modes just by definition, by taking the field and integrating it with u. So you define this light ray to be the coordinate u equal to 0. And because the field oscillates arbitrarily near u equal to 0 to near u equal to epsilon, you can take the field here and integrate it with u to the I omega, as we have done there, and you could have defined those modes and you would always find a thermal answer. Then you would say, well, why don't we see thermal radiation all around? Okay, because these modes are not the natural modes we observe. So what is special about the black hole geometry that converts these local modes near the horizon, which exist near any light ray? What gives them special significance? What gives them special significance is a global property of the black hole geometry. It has to do with the fact that these modes, which are in fact defined very close to the horizon, are also the modes that become outgoing at infinity. If I took a light ray in Minkowski space and I defined some modes at some random u equal to 0 surface, those modes would not be the modes that became outgoing on all of Scri plus. Okay, it has to do with here. It has to do with the fact that the region between u equal to 0 and u equal to epsilon at Scri plus describes a huge affine parameter. Okay? A small amount of u here becomes a very large amount of time on Scri plus. Okay, so it has to do with the fact that space, the black hole has a global property, which is it scrunches up an infinite amount of time here into a small amount of time here. Okay, that's why modes which are defined close to the black hole horizon, which you could define about any light ray in Minkowski space, become special. They gain a special physical significance of becoming outgoing modes at infinity. Okay, it has to do with this global property of the horizon, that it crunches up a large amount of time here into a small amount of time here. Okay, so let me just explain now the fourth point that I made, which is that I'm sorry, I'm writing below. I don't know how to raise this, but I'll just write some. I'm just writing a summary so you can. It is that 2-point function of near horizon modes yields thermal spectrum for outgoing radiation. Okay. So what I've written here, for those of you who can't see, I'm just going to read it out so you can write it down. Is I said that the 2-point function of these near horizon modes that we explained in point 3 yields a thermal outgoing spectrum. Okay. So the point was not that the near horizon 2-point function has this thermal nature. That is true about any light ray. It's the fact that these near horizon modes also have a global significance in the black hole. Yeah.
Is the thermal outgoing spectrum the series of modes that we should?
So here I was just drawing a random line. These modes which are outgoing near the horizon also become outgoing at infinity. They describe outgoing radiation at infinity. That would not be true in general. If I just took a light ray and I define some modes, what would happen would be, let's say I just take Minkowski space. Are you familiar with diagram Minkowski space? And I just take some random light ray, one here, and I define modes in this very small region. And they define modes in a very small retarded time on Scri plus as well. However, here modes for a very small region near the horizon describe modes that describe data on an infinite amount of retarded time at Scri plus. That's a global property of the geometry. It has to do with the fact that a small amount of u here generates a large amount of time later. You see, because that has to do with this coordinate transformation. It has to do with the fact that if I take u near 0, okay, and I push u very close to 0, that can be used to describe a large range from t equal to infinity near t equal to infinity. So u very close to 0 describes a large range here. So defining these modes near u equal to 0 is the same as telling me what's happening near, and this t is a natural coordinate to use at Scri plus. Okay. So defining modes here tells you what happens on a large amount of Scri plus. That's a feature of the black hole geometry. Okay. And then the second fact, which is just a statement about quantum field theory, although it's not usually taught this way, is that if you define modes near any light-like surface, you can repeat this calculation, you'll always find a thermal spectrum. But one light-like surface in the black hole is special because it relates in a certain way to sky plus, which is it, and that's a global property, not a local property, that it converts small regions near the surface into large regions near sky plus.
That's why if you compare photos of a JNI, we get the same gap.
Photons and scalars have nothing to do with this. This is, it's true, but all this mathematics would also just go through for photons or gravitons or for anything. You'd have to keep track of some tensor indices, but nothing significant would change. Okay, so now we've made 4 points so far. Okay, and for those of you who are not following some of the maths, please keep track at least of these points. We said something about the geometry, which is at late times you get this isometry in the black hole. Then we said, you get a horizon. The horizon is just like empty space. It's not a special region. Then we said you can solve the wave equation near the horizon. You could have actually stopped me at this point and said, look, points 2 and 3 look a little contradictory. Because at point 2 you said the horizon is not special. And in point 3 you said the near horizon wave equation simplifies. But they're not in contradiction, because if you use the right coordinates, the wave equation always simplifies in the vicinity of a light ray. Okay? Then you can use this and you can solve for the 2-point function near the horizon. Then there's a special property of the black hole geometry that tells you this 2-point function is related to a 2-point function of modes that are outgoing at sky plus. Okay? And this is what gives you the derivation of Hawking radiation. So what we have derived is that up to one integral that I haven't done for you is that if you take the black hole geometry and you demand that the 2-point function has the right short distance behavior, and you look at just the property of the geometry that small distances here get blown up into large distances on sky plus, then that leads you to the property that the outgoing modes are thermally occupied. That's what we have said so far. Thermally occupied means that, as I explained there, okay, and the temperature is related to the surface gravity, which is a parameter that we introduced earlier, but I'll say again. It's related to F prime R by 2. Remember, the surface gravity we defined earlier in the lecture is F prime R by 2. Okay, that's the derivation of Hawking radiation. That's one point more I want to make, which is I defined for you the 2-point function of these outgoing modes. You could have said, what about these A's? What happened to them? What about their 2-point function? In fact, to demand that this 2-point function, had this property was almost fixed by demanding that the 2-point function near the horizon has that behavior. Remember, by the way, to derive this 2-point function, another point I want to emphasize, we did not have to make reference to what's happening in the interior of the black hole. There is something interesting that's happening in the interior of the black hole, which if we get time to come to lecture 5, I will mention, but I might not mention, which is that, you could do a similar expansion of fields in the interior of the black hole, and then you would find that the fields outside and the fields inside were entangled. But I'm not going to, for now, we don't need that to look at the derivation of Hawking radiation. So for now, we've just looked at this field expansion outside and we've found a 2-point function for these B's. And you could have asked, what about the 2-point function for these A's? In fact, the 2-point function for these A's is not fixed in a black hole background. You can set it in various ways and you can get black holes in different configurations. If you set the 2-point function of the A's to be 0, by that I mean that you set A omega L dagger A omega prime L prime equal to 0. This is a black hole where you're not sending in anything from infinity. Okay? This is what's sometimes called the Unruh vacuum. This is called the Unruh vacuum. But you could set this 2-point function also to be a thermal 2-point function. That would correspond to a black hole which you're feeding with energy from here, from the past. You're constantly feeding such a black hole so that the ingoing flux is also thermal. That's what's sometimes called a Kruskal vacuum. So you can think of black holes which is where matter is constantly falling in. In fact, real black holes in our universe do have a 2-point function for A because there's a cosmic microwave background that's constantly falling in. Okay, so real black holes in our universe are in some version of, not even the Kruskal vacuum, but some version where there's more stuff falling in than there's stuff going out. Okay, but for our purposes, for this information paradox, we'll often think of this setup where the A's are just set in the ground state. So the A's have no occupancy and they just set in the ground state. This is called the Unruh vacuum. The A's could be also not in their ground state, but that's not important for discussing the information paradox. Okay, so that tells us this field and what the 2-point functions are. Okay, now I want to go on to the information paradox, but maybe this is a good point to pause and see if there are questions. If what I've said so far, at least those 4 points on the board are clear. Okay, those are the 4 summary points. Even if some of you have not got all the details, I hope you have at least got all the summary points. If not, maybe I can pause here and take questions and then we can go on. Yeah. Unruh vacuum just means that these modes, which are the ingoing modes, are set in the vacuum. They're set in the ground state. That's Unruh vacuum. Yeah.
Is the Unruh related Unruh radiation?
But I mean, this whole derivation is related to the Unruh effect in a way, but the Unruh vacuum is not related to. I mean, apart from the fact the same person's name is associated with them. Yeah, this is just a vacuum. It's just a definition of a state. So
We're dealing with radiation.
well, it's this derivation is like the derivation of Unruh radiation. It has to do with the fact. So there are many relations, but because sometimes you also define Hawking radiation. You also derive Hawking radiation by thinking of the simplified Unruh calculation in 2 dimensions. There are other ways to derive it. So you could say this is related to that, but the Unruh vacuum is just a definition of a vacuum, just a definition of a state. I don't even know if Unruh vacuum is a standard term or something that me and my collaborators use. Okay, so maybe there's we'll call this the Unruh vacuum, but yeah. No. There's no same procedure. The Unruh vacuum is not fixed. Look, there was something special about the U coordinate here, which is that a small amount of the U coordinate got blown up into an infinite amount of time here. Okay. There is no such thing that's special about the V coordinate. Why is there no such thing that's special about the V coordinate? What's asymmetric? No. So what's asymmetric about this? Why is the U coordinate special in that a small amount of U coordinate here gets blown up into infinite amount of time here? Why is the V coordinate not special in the same way? Any answers? So you see, the question was, why don't we repeat the same derivation for the A's and find that the A's are also occupied thermally? So I said no, because the A's and the B's are asymmetric. What did we use to get the B 2-point function of the B's? We used the fact that the B's multiplied some mode, which had the property that a small amount of the U coordinate here became an infinite amount of time here, and these were the modes that multiplied U to the I omega by K. Similarly, the A's are the modes that multiply V to the I omega by K. So you could have, but there's no similar effect for the A's. Why is that? What's special? Huh? Well, it's the fact that there is no past horizon in this geometry. There would have been such a special region for the V's, but there is no past horizon in this geometry. Okay. So if I had a past horizon, if I looked at what was called the eternal black hole, which is not this geometry, then indeed it would have to be the case that both you'd have to only look at the crustal vacuum. Okay. But the U's and the V's are asymmetric. The future horizon means that small amount of U coordinate gets blown up into infinite time here, but not similarly for the V's. And it's because there's no past horizon. The asymmetry is put in by hand. We're looking at a black hole formed from collapse, not a white hole. If you looked at a white hole, it would be a different case. Okay. Okay, are there questions about this? So are there questions about these 4 summary points? Is this clear? If it's not clear, please ask. I'm happy to clarify. Because then now we'll go on and I'm going to introduce the information paradox, and tomorrow we'll start discussing various aspects of it. Today I'm just going to introduce it. Okay, I saw some blank faces, but so you can ask me later as well. But please do. So, at least these physical points are clear to you. So, when you go look at the literature, you will find this. A lot of what I said right now is not presented in exactly the same way. There are other derivations of Hawking radiation. Hawking's own derivation was actually to do ray tracing, where he looked at rays that here and looked at where they ended up there, which is also a nice derivation. If you look at this review that I gave in the beginning, or you look at this paper, you will find more details. Okay, good. So, what have we derived so far, right? So now I'm going to erase a lot of this. So what do we need now?
And the boundary be the weak that happen.
What does that mean? There are many kind of radiation that happens from realistic black holes. In fact, astrophysicists are all the time studying, uh, things emitted by black holes, because black holes, first of all, if black holes have an accretion disk, there's all sorts of complicated phenomena around them. And there's a lot of astrophysical phenomena. Here we're looking at a black hole that's basically in the vacuum. If it's really in the vacuum and there's nothing falling in and there's no accretion disk, then it only emits thermal radiation. But realistic black holes emit all kinds of other radiation as well. Astrophysicists are all the time studying radiation from black holes, which has to do with the fact that when matter falls in, it radiates. It gets accelerated and radiates all sorts of stuff. But that has to do with the accretion disk and stuff around the black hole. If there's nothing falling in, there's nothing else to be radiated except for this. This is spontaneous radiation. Okay. Is this clear? I don't know who asked the question. Yeah. No. I said that when you look at realistic astrophysical black holes, there are often charged particles around them. When those charged particles fall into a black hole, they accelerate and therefore they radiate. This has nothing to do with anything we're discussing here. But it has a lot to do with real astrophysical black holes, which often emit radiation. Black hole itself is not emitting radiation; it's radiation from the accretion disk around the black hole. Here we are talking about black holes which are in the vacuum. Nothing is falling in, so this is the only kind of radiation. No, I am going to say that now. 1 second. Okay. Okay, so let me go on. So what have we derived so far, right? Remember, I think we have derived that black holes radiate with a temperature which is given by kappa over 2 pi. Okay, this k is not the Boltzmann constant, but it's the surface gravity. Remember, this k is f prime r by 2, f prime r h by 2. This was our definition of this k. Okay, good. Now, what do I want to say about just once. Okay. I don't have the numbers with me, unfortunately. I'm going to say some numbers from memory, which I might not. Okay. Let me say one thing, and then I don't have the answer to your. I don't have some numbers, but in my notes. But let me just introduce the notion of a black hole entropy, and then I'll say something about numbers. Okay. Remember, I think you had studied in your preschool also that black holes satisfy a first law of thermodynamics that looks like this plus work terms. Did you study this in the preschool, that there is a first law of thermodynamics? This k is the same k that appears here. Okay. So notice that this is related to the fact that du is T ds plus work terms. Okay. So in thermodynamics also we have a rule like this. Okay. These facts were known earlier, before Hawking radiation was derived. It was known that black holes have a form which looks like, obey this law, which looks like dm is kappa dA by 8 phi. Because this you can derive just by looking at the perturbations of black holes. And of course, these laws of thermodynamics have been known for a couple of 100 years, right? But before this, people could have said that this is a case of the same equations having the same solutions. If those of you have read the Feynman lectures in physics, know there's a chapter there which says the same equations have the same solutions. It sometimes happens that in different areas of physics, we find that systems obey the same equations. For instance, a spring and a mass obey the same equations as an inductor and a capacitor. But that doesn't mean that a spring and a mass are an inductor and a capacitor. It just means they obey the same equations. So somebody could have said, well, this is one equation, this is another equation. Well, it's another case in physics where you're getting the same equations. However, the derivation of Hawking radiation tells us this is not the case. This kappa over 2 pi you should really interpret as the temperature. And therefore, you should say that black holes have an entropy which is given by A over 4. Okay. So, the derivation of Hawking radiation tells you that black holes have an entropy which is given by A over 4. I think Ashok might have more to say about the entropy of or the microscopic counting of this entropy of black holes. But let me say something about numbers, okay, since that was one of the questions that was asked. So you could ask, well, for astrophysical black holes, what are these numbers like? Well, I have one number in my note, but not the temperature. So, for instance, for the sun, S is 10 to the power 76 for the sun. And I don't remember what T is, but I think it's about 10 to the minus 8 Kelvin. Okay. I don't, and this number I don't remember off the top of my head. I don't have it in my notes. Okay. But it's of the order of 10 to the minus 8 Kelvin. Okay. So if you looked at a black hole of the mass of the sun, sorry, this is not the sun, for for a solar mass black hole, what I mean is. Okay. So if you take a solar mass black hole, then it has a temperature that's very small. It's 10 to the minus 8 Kelvin. And it has an entropy that's very huge. This entropy is much larger than the entropy of normal objects that you're used to dealing with. So you should remember these numbers. This is the reason why Hawking radiation is so hard to detect, because Hawking radiation has a temperature that's much lower than the radiation of the cosmic microwave background. Okay. Because of that, this 10 to the minus 8 Kelvin, I forget if it's 10 to the minus 8, 10 to the minus 6, but whatever it is, it's much smaller than the cosmic microwave background. And because of that, it's very hard to see Hawking radiation in the fact that you have already a bath of radiation and interference effects that are much larger than this. Nevertheless, this is an important effect in principle because it tells you that, in principle, if you took a black hole and you really put the black hole in an isolated universe where there was nothing around it, then such a black hole would start radiating. Or alternately, rather than taking a solar mass black hole, let's say you took, some smaller object and you turned it into a black hole. There's nothing that prevents smaller objects from turning into black holes. And such a black hole could radiate at a much higher temperature, okay, and would radiate off in a much smaller time. For instance, if the Bermuda Triangle was really a black hole, as I sometimes get asked in public lectures, and you had ships or you had a plane that really turned into a black hole, then the plane is just about the right size of black holes that we can use to do experiments. Okay, so if a black hole was like 300 tons, then in fact it would radiate away and it would evaporate in about 5 seconds, and it would have a temperature that would be human size. You'd be able to detect it. So, if the Bermuda Triangle is really a black hole generating machine, it's a good place for us to go and do experiments on black holes. Okay. Unfortunately, it is not. But, there is nothing that prevents us from, in some time in the future, having technology that could generate much smaller black holes. But as I said, the real interest in this information paradox that I'm now about to come to is not that it's empirically important, but that it forces us to think about some properties of quantum gravity, which I'll explain in the forthcoming lectures. However, I now want to explain what the paradox is. Okay, so I'm going to explain the simplest version of the paradox, which is often the version that you get, in most popular descriptions, but it's still important enough to understand how to resolve this. It's also the way many other physicists who are not experts in it think about the paradox. So it's really important to understand this. So what we said is that, black holes obey these laws, which you should really think of as the laws of thermodynamics. So black holes radiate with a thermal temperature which is given by kappa over 2 pi. Okay. If this is so, then the Stephen Boltzmann law is, right? It tells you that if the black hole is really radiating, it must be radiating some energy. And if the black hole is radiating some energy, it must in fact be losing that energy from itself. And therefore, that the Stephen Boltzmann law tells you that if you're at a temperature which is T, so in our world, for instance, D is equal to 3, then all objects radiate with some thing which is given by the Stephen Boltzmann constant into the area into T to the power 4, if you have a black body. Now, a black hole does have a thermal spectrum, so it does look like a black body, but then there are these various gray body factors that we didn't discuss, okay, these H omega Ls and B omega Ls and so on, okay. So, after you account for those gray body factors, you get some constant which is not quite the Stephen Boltzmann constant, that's something else. And that tells you that, the black hole loses mass at a rate that's given by T to the power D plus 1 into the area. Let me be in 4 dimensions, just so all of you are happy with this. In 4D, dm by dt is equal to minus c into a into t to the 4. Okay. Okay, I'm going to phrase this paradox in 4D. So all of you are familiar with it and the D doesn't confuse. Huh? No, we live in 4 dimensions. So D, we were always in D plus 1 space-time dimensions. D was the number of spatial dimensions and everything I've said so far. Okay. So, so you could ask, black holes lose mass at this rate. Now, what is T? Remember, T is F prime R over 2. So, how does T scale for a black hole of a given mass? How does T scale for a black hole of a given mass in 4 dimensions? Remember, what was F of R? F of R was 1 minus twice m by R, right? And the horizon was at R is equal to twice m. So, if you look at F prime R, RH, this is proportional to 1 over m, right? So, the temperature of the black hole, there are some factors of 2 pi and so on that are not important. The temperature of the black hole is proportional to 1 over the mass. Right? What about the area of the black hole? The area of the black hole is 4 pi RH squared. It's just the area of a sphere. So that's just 4 pi into m squared, right? So the area is proportional to m squared. Yeah, it's really just 4 pi r squared. Yeah. Okay, so the area is m squared because RH is proportional to m, right? It's the point where this goes to 0. Is that fine? Okay. So A is proportional to n squared. That tells you that dm by dt is proportional to 1 over m squared. You see? So the black hole is losing mass at a rate that's proportional to 1 over m squared. But that tells you that in a time of order m cubed, the black hole evaporates completely. Do you see how this follows from everything we derived so far? What did we put in? We said the black hole radiates at a thermal spectrum. We calculated the temperature, almost calculated the temperature up to an integral, right? And then we said, take the temperature seriously. If you take the temperature seriously, you should use the Stephen-Boltzmann law. You don't have to use the Stephen-Boltzmann law. You can just take the field and just integrate it. Just integrate it. If you do that, you will find that, the black hole radiates. This fact is almost guaranteed. You'll find some numbers which depend on the black hole, but you don't care about them. And the temperature scales like 1 over m. Okay, by the way, this related to a question that was asked. Bigger black holes have lower temperature in flat space. Okay, if you have a heavy black hole, they have a low temperature. That's why when I said the black hole of a solar mass, solar mass black hole at 10 to the minus 8 Kelvin, if you took a jumbo jet that was much smaller, like, it was like 10 to the 24 times smaller, its temperature would be much higher. It would really be very hot. So if you took a black hole that was much smaller than solar mass, even Earth-sized black hole, it would have a temperature that was much higher, much easier to detect. Okay? So the temperature goes like 1 over m, the area goes like m squared. Why? Because the radius of the horizon goes like m. Therefore, the black hole loses mass at a rate that's proportional to 1 over m squared, with some numbers that we haven't kept track of. So there should be a minus sign also. Okay? But this says that if you just integrate this equation, you take m squared to this side, you will find that you start with a black hole of some mass in a time that's of order m cube, the black hole will evaporate away completely. Okay? Is this clear? This follows from the derivation that we have almost completely done except for one integral. Okay? Okay. So this brings us to the first version of the, well, actually, let me keep this here. Let me keep this here, actually. No. This brings us to almost to the first version of the paradox, simplest version of the paradox, and then we'll discuss other versions, which is the following. Look, let's say we start with a black hole. Okay. Then what Hawking said was, Hawking said a little bit more. Okay, we'll discuss what he said that was more, which had to do with the interior and tracing out the interior and so on. But this is the simplest version of the paradox. Take the black hole, take a black hole, put it in isolation. So we are not in our universe, we are an imaginary universe. There's no radiation falling into a black hole. Black hole just exists in isolation. Or we have a black hole it's very hot, made of a small object. And this black hole, in some time, if you leave it, it starts spontaneously, due to quantum effects, emitting Hawking radiation. We calculated the spectrum of Hawking radiation. We found it was thermal. You can integrate it, and you would find that this Hawking radiation integrates to give you some overall emission of energy from the black hole. Since the total energy must be conserved, whatever energy comes out in radiation must be lost from the black hole. Right? Because the black hole is emitting at some rate, that must be the rate of loss of mass of the black hole. The rate of loss of the mass of the black hole is proportional to 1 over m squared, which tells you as the black hole loses mass and becomes of smaller mass, the rate of mass emission actually increases. Okay, so the rate of mass emission goes to infinity as the mass goes to 0. And therefore, in a time that's proportional to m cube, the black hole evaporates completely. Okay. So, however, what is left after the evaporation? What is left is the radiation that it emitted. The radiation that emitted is still up on the board. It is these B modes. Okay. But it looks like these B modes are in a thermal spectrum. We know the 2-point function of the B modes is. So it looks like that after evaporation, we are left with excitations of these B modes, whatever, we are left with these B excitations, which are thermal. Well, this is a paradox. Why is this a paradox? This is a paradox because it looks like what Hawking is saying, that I could have started off with two different kinds of black holes. Maybe I have two stars. One star had a greater percentage of hydrogen. Okay, this was, I don't know if realistic stars have this. Okay, I'm going to make up some percentage. Maybe this had 90% H and 10% helium. Okay, and this was also, I don't know. Since I don't want a star, maybe I'll take it to be 10 to the 20 kg. It's not a star, it's some other object, okay, which is made up of this. I'll take something else which is also 10 to the 20 kg, so it will evaporate fast. And this has, I don't know, it has 50% hydrogen and 50% helium. Okay. I'm just making up these numbers, okay, they don't mean anything. I'm just meaning that you can start with black holes that have the same mass and that have different compositions. Okay. But what did the surface gravity and the temperature depend on? It only depended on the total mass, you see. So the surface gravity is the same for these two black holes. In fact, and so they'll keep radiating at the same rate. And the mass will remain the same at all points. So it looks like the radiation will be the same. So I take these, they form a black hole. So this forms black hole 1. This forms black hole 2. But after some time, both of them radiate, but the radiation is the same. It looks like it's the same. In both cases, we get excitations of these B modes, which give you some radiation. Well, now we are in trouble because it looks like these time evolution arrows can't be reversed. It looks like we could start from two different initial states. In fact, an infinite number of initial states. I could put as many different boxes as I like here while keeping the total mass conserved. I could start with many different compositions and I would lose all information of that composition in the end. In the end, I would just be left with some photons or gravitons or whatever other light fields that are in the universe. Okay. So it looks like I can start from different initial states and end up with the same final state. And this is a problem because in quantum mechanics, time evolution is always unitary. Not just in quantum mechanics, in classical mechanics, it's a sacred principle of physics that given all details about a final state, you should be able to compute all details about the initial state. Okay, so time evolution is unitary. This is very important, right? Okay. And it looks like this is violating that. because it looks like, and I want to emphasize at all point, it looks like this is a false, this paradox is going to be particularly easy to resolve. It looks like we have computed the final state. In the final state, we have quantum fields which give us a microscopic description of what's happening, and we've computed the state of the quantum fields. Okay. And so this looks like a paradox. And so this is the simplest version of the information paradox. We will see in the next lecture how to fix this version of the information paradox and how there might be refinements of it. But this is the simplest version that we've derived. Okay, I've run out of space on this board, but the fifth point that I wanted to make is, which you should all keep in mind, is that, and this is there are at least 5 points that we made today. Please keep all these 5 points. I hope you understand, which is, and then I'll stop. Thermal radiation causes black hole to evaporate into a final state independent of initial conditions. Evaporate into a final state seemingly independent of initial conditions. And this is a paradox. Because if you start with an initial state and end up with a final state that doesn't, that's independent of the initial state, that's a paradox. Okay, so this is the fifth point, and I'll stop here because, in fact, I already ran out of time. So let me just summarize everything we said. We made statements about the classical geometry. We looked at the wave equation. We derived the form of Hawking radiation up to one integral. I tried to explain what the physics of that was. Once you've got the form of Hawking radiation, then it's pretty clear that Hawking radiation would lead to loss of energy from the black hole, because we expect energy is conserved. Therefore, you lose energy. You lose energy at this rate, which is proportional to 1 over m squared in 4 dimensions. That tells you that in the time that's proportional to m cubed, the black hole evaporates away completely. And this suggests that the calculation that we've done so far suggests that the final state is just excitations of these B modes, which doesn't care about what the details of the initial state that went into the black hole were. And that had to do with this fact, this first geometric fact that we pointed out. It had to do with the fact that the Hawking radiation was coming from a region of space-time which didn't care about the infalling matter. So the way we do this is we take a black hole, we let it evaporate, we let it sit, let it form, we wait for a long time. After a long time, the black hole starts emitting radiation which is independent of the infalling matter. And that radiation, so this geometric fact we noted at first time was important. At late times, the horizon is empty, so it doesn't have details of the infalling matter. That is why the final state we are getting looks like it is independent of the initial state. Okay, so all the 5 points that we mentioned are interrelated, and they lead to this paradox. Okay, so I'm going to stop here, and we can take some questions, and then we'll go on with how to resolve it. As I said, even if you didn't understand all the equations, I hope you understood these 5 bullet points. Okay, so I'll stop here and take some questions.
Could you explain again what the deal was with the infinite number of modes of the photon near the radiation?
It had to do with the fact that we defined these modes by doing an integral near u equal to 0. And usually when you've defined modes in quantum field theory, you do an integral on a whole spatial slice. Why are we able to define these modes near u equal to 0? It's because these modes are defined as a coefficient of u to the I omega by k. So they oscillate an infinite number of times near u equal to 0. So doing this Fourier transform from u equal to 0 to u equal to epsilon, which is explained more in the paper that I referred you to, actually is already enough to extract the mode to good accuracy, because the mode oscillates a very large number of times. That's why you can define this mode. You can get this 2-point function by doing an integral very close to the horizon. You can in fact do this for any light-like surface. You can always define some mode which you call a near horizon mode for any light-like region. Usually that mode has no significance. It has no physical significance. However, in the case of black holes, the modes that you get by integrating near u equal to 0 has significance, because they are the modes that also become outgoing at infinity, and these are the natural modes to use at infinity. That's why deriving this 2-point function lets you get a 2-point function at infinity.
Is that particularly dny d portion of the mass, is that the reason why the surface gravity sort of goes, so I forgot what you mentioned, surface gravity decreases as we
No, surface gravity is defined independently. Remember how we defined the surface gravity? We defined it as, yeah, remember, the point is that, no. So we defined the surface gravity as F prime R by 2. This is just given by M over R squared. Look here, in 4 dimensions. So M over and R is equal to M. So it's always 1 over M.
I think you mentioned that the surface gravity decreases or increases as the black hole mass.
Yeah, it's here, no? This is the surface gravity. But it comes from here. F prime R is 1 over M. Fr is 1 minus twice M by R. F prime RH. F prime R is twice M by R squared. You put R equal to M. You get F prime RH is 1 over M. And maybe I'm being inconsistent with small m and big M, but there's some factors. It's clear? Yeah.
As I understand, these correct can talk. We don't have any information about the matter inside the black hole state, that the state of the matter inside with that. We don't have any information about it or the major of the statistics. So, how can you interpret the entropy of black hole?
The entropy is a different. Ashok will give many lectures on how to understand the entropy of the black hole. What I said about the entropy just came from the first law of thermodynamics. Because there's a first law of thermodynamics and you can define a temperature, you can also define an entropy. Because du is equal to TdS, if I identify T, I can define an entropy. How you count this entropy and how you interpret it is subject of a different lecture. However, this entropy is roughly thought of as the number of microstates that correspond to a black hole with that macro state. So black hole with a given micro state from outside just means, its mass and charge and angular momentum. You can ask how many different microstates are there in a microscopic theory that give you that kind of a black hole. So in string theory, for instance, we can count the microstates and that you will get this answer. Okay, but this is a completely different, counting the entropy is an orthogonal topic from this issue of evaporation. This entropy you can also, it's a statistical entropy.
So our paradox arises from the fact that the initial potential that we put in at first to the black hole moving.
From those points 1 and 2 there. That at late times you get a T goes to T plus delta T isometry and the horizon doesn't have any details of the initial state. And from there we went on to derive the Hawking radiation, right? But we never made reference to the initial data because we just got rid of it in the beginning. So this fact I was saying of 90% hydrogen and helium, it didn't appear anywhere in the derivation. You could have asked why it didn't appear because we got rid of it in the first step. By saying that, at late times we don't care and that's where the Hawking radiation is coming from. That's why I said all these 5 bullet points are interrelated. No more questions, everyone's tired. Yeah. Yeah, because it's obviously not going to be true, right? If it was true, we would really have a paradox with quantum mechanics. So obviously we've made some mistake in this reasoning. Yeah, so that's why it's seemingly independent because this is wrong. This conclusion is wrong, right? You should how could it be right? If it was right, we would have trouble. So this is a wrong conclusion. So the question, that's why, so I haven't told you what the mistake is, but there's a mistake here, obviously.